And we're back for the exciting conclusion of 10.4, where we're learning about the convolution. Another important property of the Laplace transform is that the Laplace transform of little f of t over t is equal to the integral from s to infinity of capital F of sigma d sigma. But so that I don't mix things up, I'm going to call the dummy variable, I'm going to call him x. Okay. Some people will just go ahead and call him s and just realize that we're going to put in the s anyways. But anyways, you can use whatever dummy variable you like. So let's go ahead and find the Laplace transform of this guy. So we need the Laplace transform of 1 minus cosine of 2t over t, okay? Which, if we notice, I need to find the Laplace transform for 1 minus cosine of 2t, and that would be my capital F of s. And if I could find out what he is, I could then take this nastier thing and turn him into something that's a little bit easier to handle here. And we know that the Laplace transform of 1 is 1 over s, and the Laplace transform for cosine of 2t is s over s squared plus 4. So the Laplace transform for 1 minus cosine of 2t over t would be equal to the integral from s to infinity of, and so this is capital F of s, and I'm actually going to use, so I don't mix up my variables, I'm going to use x. So capital F of x would be 1 over x minus x over x squared plus 4. Okay, so we're going to have the integral of capital F of x dx, which is 1 over x minus x over x squared plus 4 dx. Okay, this first part is going to be pretty easy to integrate. He's just a natural log. The second part is going to be a little bit harder, but we can do him. Let's try a little u substitution. Let's let u equal x squared plus 4. Therefore, du would equal 2x dx. And if I divide by a 2, x dx would be a half of du. So we'll do the indefinite integral, and then we'll switch back to our original limits so that I don't have to do that right now. So we're going to get equals the integral from s to infinity of 1 over x dx minus, we'll do an indefinite integral, and I promise we'll switch back, x dx, the numerator here is du, and we have a 1/2, and u down here. Okay, so that's looking a little nicer. And so this guy is going to be, we're going to need to do a limit as b approaches infinity of the integral of 1 over x dx is natural log of x. And we're going to evaluate that from s to b. And we're going to then do minus 1/2 natural log of u, technically absolute value of u, but since u is x squared plus 4, it can never be negative, so absolute values wouldn't make any difference here. So natural log of u, okay. And then I'm going to go back to my original variable. So we're going to get the limit as b approaches infinity of natural log of x from s to b minus 1/2 natural log of u, which according to our substitution was x squared plus 4. And we also evaluate that from s to b because of my indefinite integral. Or sorry, switching back to the definite integral. So let's see what we get here. We could do this a couple of different ways. So let me just do it the most straightforward. So we got the limit as b approaches infinity of um, yeah. Let's go ahead. I noticed that I'm evaluating between the same limits and I've got natural logs. So I'm going to remember a couple of my properties of logarithms. One of the properties is natural log of A minus natural log of B is equal to natural log of A over B. And the natural log of x to the pth power is p times the natural log of x. So I'm going to use those two properties to make this be a little bit friendlier looking. So we're going to write them. So we're going to bring this constant out here in as a power using this property. And then the difference of logarithms is the quotient of the two arguments. So we're going to get the natural log of x over x squared plus 4 to the 1/2 power, evaluated from s to b. And let's go ahead and do that. So that will give us the limit as b approaches infinity of natural log of b over square root of b squared plus 4 minus, I'm going to have to weasel just a little bit, natural log of s over s squared plus 4 inside of a square root down there. Okay, well, one thing that we do know is that the limit as b approaches infinity of b over the square root of b squared plus 4 would be equal to the limit as b approaches infinity of the square root of b squared on the top, since it's a positive number. And so we could write that all as square root of one whole big thing, b squared over b squared plus 4. And at any rate, this all, as b gets super ginormous, this goes to 1. And therefore, the innards here go to 1. And the natural log of 1 is 0. So, our final Laplace transform then works out to be negative natural log of s over square root of s squared plus 4. But we could even use this negative, that's a negative 1, and we could bring him in as a power here and write that as natural log of square root of s squared plus 4 all over s. Okay. All right. Let's take a deep breath. And let me let you try this guy, and I'll work on him and we'll step through him quickly after we come back from our pause. Pause. All right, so now you've had a chance to work on him. Let's see what we do together here. So remembering that if we take the derivative of this guy, because right now he's nasty, I don't know how to handle him just straight up. But if I do his derivative, I'm going to need to do 1 over the innards times the derivative of the innards. And when I simplify that, okay, remember that s to the negative 3 is 1 over s cubed. And then if I multiply the s cubed here, I'll get s cubed plus s, which factors on the bottom as s times s squared plus 1, which is nifty because that actually breaks down as a product of known inverse Laplace transforms. So we can, like we saw with our theorem earlier, that f of t is equal to negative 1 over t times the inverse Laplace transform of f prime of s. We now know what f prime of s is. So we've got negative 1 over t, inverse Laplace transform of that, which breaks down into two easier to manage pieces. So I can use my convolution. And so it's going to be negative 2 convolution t, sorry, negative 2 times the convolute sine of t, and we have a negative 1 over t out front. But we saw that the convolution is commutative because we'd like the second thing to be easier. And what's easier than a constant? Not much. So we'll stick with him. And we'll do the definition of the convolution here. And let me bring the negative 2 factor out front. So we got 2 over t integral from 0 to t of sine of x dx, which we can integrate and evaluate between our limits of 0 to t. So doing, we get, when all is said and done, 2 over t times negative cosine of t plus 1. And if we distribute that through, we get negative 2 over t cosine of t plus 2 over t. And that concludes our convolution and his wonderful theorems.